Suspension systems. Like the rest of the systems on cars and light trucks, the suspension system has greatly changed through the years. Not only has technology brought about these changes, so has the quest for great handling and comfortable vehicles. Suspension systems for the front and rear of a vehicle can get quite complex. The reason suspension systems are complex is that they perform a very complicated function. These systems must keep the vehicle's wheels lined up with the travel of the vehicle, limit the movement of the vehicle's body during cornering and when going over bumps, and provide a smooth and comfortable ride. Frames. To provide a rigid structural foundation for the vehicle body and a solid anchorage for the suspension system, a frame of some type is essential. Conventional frame construction. In the conventional body-over-frame construction, the frame is the vehicle's foundation. The body and all major parts of a vehicle are attached to the frame. It must provide the support and strength needed by the assemblies and parts attached to it. In other words, the frame is an independent, separate component because it is not welded to any of the major units of the body shell. Unibody construction. This type of construction has no separate frame. The body is constructed in such a manner that the body parts themselves supply the rigidity and strength required to maintain the structural integrity of the car. The unibody design significantly lower the base weight of the car, and that in turn increases gas mileage capabilities. Suspension system components. Most automotive suspension systems have the same basic components and operate similarly. Their differences are found in the method in which the basic components are arranged. Springs. The spring is the core of nearly all suspension systems. It is the component that absorbs shock forces while maintaining correct riding height. If the spring is worn or damaged, the other suspension elements shift out of their proper positions and are subject to increased wear. The increased effect of shock impairs the vehicle's handling. Various types of springs are used in suspension systems: coil, torsion bar, both mono and multi-leaf types, and air springs. Springs are rubber-mounted to reduce road shock and noise. Automotive springs are generally classified by the amount of deflection exhibited under a specific load. This is referred to as the spring rate. According to the law of physics, a force or weight applied to a spring causes it to compress in direct proportion to the force applied. When that force is removed, the spring returns to its original position, if not overloaded. Remember that a heavy vehicle requires stiffer springs than a lightweight car. The springs take care of two fundamental vertical actions: jounce and rebound. Jounce occurs when a wheel hits a bump and moves up. When this happens, the suspension system acts to pull in the top of the wheel, maintaining an equal distance between the two front wheels, and preventing a sideways scrubbing action as the wheel moves up and down. Rebound occurs when the wheel hits a dip or hole and moves downward. In this case, the suspension system acts to move the wheel in at both the top and bottom equally, while maintaining an equal distance between the wheels. The spring goes back and forth from jounce to rebound. Each time jounce and rebound becomes smaller and smaller. This is caused by friction of the spring's molecular structure and the suspension pivot joints. A shock absorber is added to each suspension to dampen and stop the motion of spring after jounce. All of the vehicle's weight supported by the suspension system is known as sprung weight. The weight of those components not supported by the springs is known as unsprung weight. The vehicle's body, frame, engine, transmission, and all of its components are considered sprung weight. Undercar parts classified as unsprung weight include the steering knuckles and rear axle assemblies, but not always the differentials. Keep in mind that, in general, the lower the ratio of unsprung weight to sprung weight, the better the vehicle's ride will be. Coil springs. Two basic designs of coil springs are used, linear rate and variable rate. Linear rate springs characteristically have one basic shape and a consistent wire diameter. All linear springs are wound from a steel rod into a cylindrical shape, with even spacing between the coils. As the load is increased, the spring is compressed, and the coils twist, or deflect. As the load is removed, the coils flex, or unwind. As the load is removed, the coils flex back to the normal position. The amount of load necessary to deflect the spring 1 inch is the spring rate. On linear rate springs, this is a constant rate, no matter how much the spring is compressed. For example, 112 kilograms compress the spring 25.4 millimeters, and 340 kilograms compress the spring 76.2 millimeters. Spring rates for linear rate springs are normally calculated between 20% and 60% of the total spring deflection. Since heavy-duty springs are designed to carry 3 to 5% greater loads than regular-duty springs, they are somewhat different. The first difference that can be noticed is wire diameter. On heavy-duty springs, wire diameter can be to 0.1 inch, or 2.5 millimeters greater than the regular-duty spring for the same application. The other difference is free length. A heavy-duty spring is up to 2/2 inches, or 64 millimeters shorter than a regular-duty spring for the same application. The important factor to remember is load-carrying capabilities. Variable rate spring designs are characterized by a combination of wire size and shapes. The most commonly used variable rate springs have a consistent wire diameter, are wound in a cylindrical shape, and have unequally spaced coils. This type of spring is called a progressive rate coil spring. The design of the coil spacing gives the spring 3 functional ranges of coils: inactive, transitional, and active. Inactive coils are usually the end coils, and introduce force into the spring. Transitional coils become inactive as they are compressed to their point of maximum load-bearing capacity. Active coils work throughout the entire range of spring loading. Theoretically, in this type of design, at stationary loads the inactive coils are supporting all of the vehicle's weight. As the loads are increased, the transitional coils take over until they reach maximum capacity. Finally, the active coils carry the remaining overload. This allows for automatic load adjustment while maintaining vehicle height. Another common variable rate design uses tapered wire to achieve this same type of progressive rate action. In this design, the active coils have a large wire diameter, and the inactive coils have a small wire diameter. The latest designs of variable rate springs deviate from the old cylindrical shape. These include the truncated cone, the double cone, and the barrel spring. The major advantage of these designs is the ability of the coils to nest, or bottom out, within each other without touching, which lessens the amount of space needed to store the springs in the vehicle. Unlike a linear rate spring, a variable rate spring has no predictable standard spring rate. Instead, it has an average spring rate based on the load of a predetermined spring deflection. This makes it impossible to compare a linear rate spring to a variable rate spring. Variable rate springs, however, handle a load of up to 30% over standard rate springs in some applications. Servicing coil springs. A user must know how to check and replace coil springs, select the proper replacement, and recommend the proper size and type of spring to the customer. The first step in coil spring selection is to check for the original equipment part number. This is usually on a tag wrapped around the coil. In many instances, This tag falls off before replacement necessary. If a set of aftermarket springs has been installed, the part number might be stamped on the end of the coil. Next, check to see what type of ends of coil springs have. There are 3 types of ends used in automotive applications: full wire open, tapered wire closed, and pigtail. Springs with full wire open ends are cut straight off, and sometimes flattened, or ground into D or square shape. Tapered wire closed ends are wound to ensure squareness, and ground into a taper at the ends. Pigtail ends are wound into a smaller diameter at the ends. The final step is to check the application in the catalog. To do this, it is necessary to know the make, year, model, body style, engine size, number of cylinders, and if the vehicle is equipped with air conditioning. In some cases, it is also good to know the type of transmission, seating capacity, and other specifics that add extra weight to the vehicle. In most catalogs, springs are listed by vehicle application in 2 sections, front and rear.